hope all of you healthy today. Unfortunately, we have to do the online class again. Yeah, hopefully things are going to be better next week. Yeah, okay, but that's fine. We will try to have this class as maximum as possible. All right. This is the code for today's class. So you can insert this code in Presency. Okay, so now today we will continue. We will start the class, with the first topic, which is about the internal combustion engine. So last week we have learned about we've done some review on what are the basic equations that are used in energy conversion. Yeah. So we have lots of theoretical background before in thermodynamics and fluid mechanics, and today again we will learn about internal combustion engine, and you have learned about this before. Yeah, so this is not a new thing for you as well for the internal combustion engine, but we will look at something different. Yeah, so we will look at the performance. Yeah, perhaps what you have done is about the theoretical background, the principle of the work. Yeah, so that now we will extend that further in the performance of the internal combustion engine. Okay, so I'll stop this one. Right, so yeah, in the book, yeah, this will be in chapter 3, in the book of mesin konversi energy, in which we are going to talk about internal combustion engine, and this will cover the spark ignition engine and also the compression ignition engine. Okay, so when we look at the classification of the internal combustion engine, we have the rotary engine, in which this is actually similar to the reciprocating engine, only the shape is different. Yeah, the shape of the engine is different. So in rotary engine, we often have Wankel engine. And for reciprocating engine, we have the spark ignition engine, or usually we call that as gasoline engine. Yeah, gasoline engine. And we also have compression ignition engine, which is usually called as diesel. Yeah. So that we have diesel engine as well. And last, we will talk about dual cycle engine. Yeah. Okay. So when you learn, when you think about internal combustion engine, you might have the diagram on your mind, for the cycle. But before that, we will see some introduction on that, including the processes in the cycle. And also we will learn about the open cycle gas turbine. And you have learned this as well, yeah. Okay, so this is the shape of Wankel engine. And basically, this is similar to the reciprocating engine. The difference is that now it's not having a upward and downward movement of the head of the piston, but instead now using a rotation. Yeah. So there is a rotation here, so that when it rotates, so that we have here, for example, this is the intake, and then we have an area here. So this is the volume. Yeah, the volume when it rotates, because it has slightly triangular shape like this one, so that it will compress the volume when it rotates. Yeah, so initially the volume is here, at the intake, and then it will be compressed when it rotates. So when it's compressed, the volume becomes very small, so that the pressure increasing. Yeah, when the pressure increasing, so that we can ignite it, so that afterward it will have a power process, or expansion process, and then it will have a larger volume here, and then it will releasing the exhaust gas. Yeah, so basically similar. Yeah, so the processes are the same. The difference is only the shape of the engine. So this is for Wankel engine. Yeah, so we can see here that we have initially here we have an intake process, and then we have a compression, and then we have the burning process here, yeah, combustion, and then we have an expansion and releasing the gas, yeah, the exhaust gas. Okay, so this is for Wankel engine. And for the piston engine, I think this is not new as well. We have learned about that, in which we have, for example, in this case, we have 4 cylinders, yeah, in the engine block. So we have 4 cylinders here, in which we have also the camshaft here, and it will regulate the movement of the valve. Yeah, so we have the intake and the exhaust valve, so that when it rotates along with the movement of the crankshaft here, so that it will regulate the opening and the close of the valves. Yeah. So we see here that we have 4 engines in a row. Yeah. So this is inline. So this is the example in which last week we also have done some review on internal combustion engine. Yeah. So basically there are four processes. Yeah, 4 processes in the internal combustion engine for a cycle, for one cycle. So what are the processes in a cycle? Yeah, what are the processes? So that will be similar, yeah, similar to the Wankel engine as well. So that we will have an intake process, yeah, and then we have a compression, yeah, and after the compression we will have the combustion, yeah. So that will be the power, yeah, power process or expansion process. And then we have it released for the exhaust gas. Yeah. So we have intake, compression, combustion, and exhaust. Yeah. So this will regulated by the camshaft here. Okay, so these are the processes in which, yeah, we can see we have the intake, yeah, and then we have the compression, the power, yeah. So this is compression, and then we have power, and then exhaust, yeah. So in this case, is it a 2-stroke or 4-stroke engine? Yes. Yeah.
It's 4-stroke engine, ma'am.
Yeah, 4-stroke engines, because it needs 4 movement for a complete cycle. Yeah, 4 movement for a complete cycle. Yeah, so that is correct. Okay, so these are the components. Yeah, we have for the gasoline engine, for 4-stroke gasoline engine, we have here we have the piston. Yeah, so this is the piston, and then this is the head of the piston. So then when it moves upward and downward here, so the volume inside the cylinder will change. Yeah, and we have the spark plug here. Yeah, so when we want to determine whether this is gasoline or diesel, yeah, so gasoline will always need a spark plug. Yeah, so we have a spark plug here, and then we have the valve. Yeah, so we have the valves here. So this will be the intake, and this is the exhaust valve, and this is regulated by the camshaft. Yeah, so that we have the inlet camshaft and the exhaust camshaft, and we have the connecting rod here. Yeah, to connect the movement of the piston to the crankshaft. Yeah. And here we have the water jacket, which surround the cylinder to cool the temperature of the piston, so it will be not too high. Yeah. Okay. So that again, when we want to learn about piston engine, so we have several terms that will be used. Yeah. So I think you still remember here when we have a piston, so then we will have the maximum volume will be shown at the line here, which shown the bottom dead center. Yeah. So this is the bottom dead center that will be when the piston moves to the bottom dead center, it means that the volume inside the cylinder will be maximum. Yeah. And when the head of the piston moves up, move up here, up to the minimum volume, which is shown by the line of the top dead center. And the distance here is called the stroke. Yeah, so stroke here is the step or the length, in which the head of the piston will move minimum to the maximum point. Yeah, so this is called a stroke. So that's why when you say there is 2-stroke or 4-stroke, it means that for a complete cycle, it needs 4 strokes of movement. And for the diameter of the cylinder, we often mention it as bore. Yeah, so this is the bore diameter or the cylinder diameter. Yeah, this is the bore. This will be the diameter. And when we want to see here the volume here, so we have we name the minimum volume here. Sorry, we name the minimum volume here, in which this is the volume when the piston stay at the top dead center. So this minimum volume is called as the clearance volume. Yeah, the clearance volume. So that will be the minimum volume when the piston at the maximum point. Yeah. And when it moves down, so that we have the term of displacement volume. So the displacement volume is the volume that is displaced during the stroke. Yeah? So the displacement volume is the total volume minus the clearance volume. Yeah, so this will be the displacement volume. So if we want to find the displacement volume, that will be the bore diameter. Yeah, so that will be, if this is a cylinder, yeah, so that we have an area of the cross sectional of the piston. So that will be pi d squared. Yeah, pi d is the diameter of the bore squared, and that will be multiplied by the stroke. So that will be the displacement volume. Yeah, so displacement volume is the volume that is displaced during the stroke. Yeah, the volume that is removed, yeah, or displaced. So then when we define the compression ratio, so that will be the ratio of the maximum volume over the minimum volume. Yeah, the compression ratio is V max over V minimum, or the volume at bottom dead center over the volume at top dead center. Or when we can write it down like this one, so that the volume, the minimum volume will be the clearance volume. Yeah, so that will be the clearance volume. And the volume at the bottom dead center, that will be the total volume. Yeah, the total volume. Or we can also write it down here as the total volume will be the displacement volume, yeah, plus the clearance volume. And this is divided by the clearance. Okay, so this is to define the compression ratio. Yeah. All right. So when we talk about the energy, yeah, so we have an energy, and we will remember that in the actual case, yeah, in the actual case, when we have a process, yeah, we will have a loss. We will have losses, yeah. So we see here that, for example, we have fuel, yeah, which is injected in the cylinder, so that the fuel will have energy, yeah. So that will be the energy of the fuel, the energy content of the fuel. So that when it's burned, yeah, when it burned, of course, not all of the energy of the fuel can be utilized. So we have some energy losses here, which is this is dealing with the irreversibilities of the process. Yeah, we have the exhaust losses. Yeah, we know that when the exhaust gas goes out from the cylinder, yeah, from the combustion chamber here, yeah, from the piston, we know that there will be losses. Yeah, so the exhaust gas may bring some energy level. And also we have coolant. So when we give cooling, we have energy loss as well. And also losses in terms of radiations. So it means that when we have the fuel is burned, yeah, we already have energy losses. So that thermodynamically, we will have the energy that can be used in the process, the next process is actually the indicated energy. Yeah. So this will be the indicated energy. Yeah. So from the irreversibilities that occur in the process, so what we have here, which is initially energy and fuel, now becomes indicated energy. Yeah. And then afterwards, the energy here will be used to move the piston downward and upward. Yeah. So here, the energy here will be used to drive the crankshaft. Yeah. Later it will be used to drive the crankshaft. And we see here that there is a mechanism here. Yeah. So this is a mechanical process. Yeah. So there is a change from thermal energy. Yeah. Into mechanical energy. And during this process, we have another energy loss, which is relates to friction. Yeah, we know when we pushes the piston downward, so there will be friction on the sides of the piston head. Yeah. And we also have energy losses for pumping and so on. Yeah, so this is dealing with mechanical, so that here later what we can use, yeah, what is the power that is used to driven the crankshaft or the useful energy, this will be here. Yeah. So that we see here that during the process, because we have energy losses, so that means we have efficiency, yeah, for the process, for each of the process here. So we have here the thermal efficiency, yeah. So the thermal efficiency, if we talk about thermal efficiency, so that will be the ratio between the indicated energy, which is IHP, yeah, the indicated energy, over the energy of the fuel, yeah, or we can say that to be the power of the fuel. So that will be the thermal efficiency. And when we talk about mechanical efficiency, yeah, mechanical efficiency, so that will be the efficiency, yeah, so that will be the ratio between the useful energy, yeah, and usually we set the useful energy to be the brake power, yeah, brake power. So this is the useful energy. So that when we look at this, so the mechanical efficiency here will be the brake horsepower over the indicated horsepower. Yeah. So we see here that we have several losses. And when we want to compare this energy, this useful energy, to the initial energy, the total initial energy that is contained in the fuel, so that we have the terms of the thermal brake efficiency. Yeah, the thermal brake efficiency. So that will be BHP over the power of the fuel. Yeah. Okay. So we see here that we have several steps. We have several losses here. Yeah. And usually the energy losses to friction here is called to be FHP or friction horsepower. Yeah. So this is the losses. So then when we look at the difference between BHP and IHP, yeah, so that we can say that FHP here is the difference between IHP and BHP. Yeah, so that will be the friction loss, yeah, or friction horsepower. So this is the losses due to friction. Okay, so that if we want to increase the efficiency, we want to minimize all of the losses that it occurs during these processes, yeah, during the transfer of energy, during the transfer of power. Right, so this will be the energy flow, yeah. And the main, yeah, usually when we talk about the useful, the energy that we can use, yeah, will be the brake horsepower. Yeah. All right. So this is the energy. Yeah. And this one as well, similar. So that we see that is a step of energy reduction throughout the process. Yeah. When we transfer the energy from the fuel, yeah, with thermal and then mechanical up to the useful energy, we have several reduction here. Or again, if you want to look at like this, yeah, so this will be the fuel energy or the fuel power, which is injected to the piston, yeah, to the cylinder piston, and then we have the indicated thermal, indicated power, and then from the indicated power, it will be shaft power or the brake power here with a reduction because of friction in the process, yeah. So that if we want to find the total, yeah, the total, that will be the multiplication as well, yeah. So if we look again back here, yeah, so that the efficiency, the optic efficiency, for example, is PHP over the power of the fuel. Or we can write it down this as PHP over IHP multiplied by IHP over P, similar, yeah? So we can cross that out. So that will be PHP over the power of fuel. Or we can write it down here as PHP over IHP. Here is the mechanical efficiency, and IHP over the energy of fuel or the power of fuel, that will be the thermal indicated efficiency. Yeah. Or if we want to find the overall efficiency, we can just multiply the efficiency here during the transfer process. Yeah. So that will be the same. So the overall efficiency will be the multiplication. Yeah. So if you look at here, that will be the multiplication. And if we have, for example, the combustion efficiency, so that we can multiply that. Okay, so that will be the overall efficiency for the engine. Okay, so that what is actually the definition of indicated horsepower? Yeah, so we can use the term of IHP, or sometimes we use the term of NI. Yeah, I here it, or sometimes we write it down as PI. Yeah, so that is indicated power. So this is actually the total horsepower actually developed on piston in the engine. Yeah, so this is due to the thermodynamic or chemical combustion. Yeah, and brake horsepower here is the power from an engine. Yeah, and friction horsepower here is the difference. Yeah, the difference between indicated horsepower and brake horsepower. Yeah, so this is the energy, the power loss because of friction. Yeah, friction, and what friction is here? So the friction occurs in the bearing. Yeah, because when we have rotating shaft, crankshaft, and so on, we have bearing. So there will be friction in bearing as well, and also in the piston and other mechanical part of the engine. Also the movement of the engine, yeah, of the head of the piston, and also induction of the fuel air charge and delivery of the exhaust gas. Yeah, so when we flow the exhaust gas out or take the the air charge in to the engine, so there will be friction as well. Yeah, so this friction horsepower. So that, yeah, this is still mixed up, yeah, between English and Indonesia. Not all of here in the slide is already in English, yeah. So that we have IHP is PHP plus FHP, yeah, or we can say that the friction horsepower will be equals to IHP, the indicated power, minus the brake horsepower. And the theoretical power from fuel consumption, in which we say before as P fuel, yeah, P fuel. So that will be, this should be M dot, yeah, the power of the fuel, yeah, because we talk about power, so that will be M dot times H. Yeah, so this is the power of the fuel. So this will be the total energy that is provided by the fuel. Now, what is HV here? What is HV? Yeah?
Maybe kind of internal energy, ma'am.
Yes, yeah. So it's the energy content, yeah, the energy content, or what it stands for?
U, ma'am.
Huh?
Maximum biasanya disimbolkan U, ma'am.
Yeah, internal energy. Yeah, HV stands for heating value. Yeah, so that's heating value. Yeah, or energy content. Yeah, so if you look at which one is that? This is the efficiency, or we will look at again at that later. So heating value. So this is the heating value or the energy content. Yeah, or energy content in the fuel. Yeah. Okay. So yeah, so this is so looking at this, we can calculate the efficiency, yeah. And we know the value of the power at each step, yeah, during the transfer of the power. Now also if we look at the theoretical efficiency, which is the cycle efficiency, and this is based, yeah, or the theoretical efficiency is shown here. I will go back to the first slide here, yeah. So when we look at here, yeah, we have the efficiency in which, yeah, this is dealing with the thermodynamics process question. So the theoretical efficiency here, yeah, so back again there. So this is specified by this one, yeah, and this is what we have from thermodynamics, yeah. So the theoretical is cycle efficiency, in which this is a function of the compression ratio and the method of the combustion. So I think you have seen these equations before in thermodynamics, yeah, in the second thermodynamics, in which we can calculate the theoretical cycle, yeah, that will be 1 minus 1 over R K minus 1. Yeah. Well, we have for the diesel cycle, yeah, auto here, back again, auto cycle is gasoline engine, yeah. For gasoline engine, the cycle is called to be auto cycle, yeah. And for diesel engine, we have diesel cycle. So this is 1, yeah, 1 minus 1 over RK minus 1. And that will be the cutoff ratio as well, yeah. So we have the cutoff ratio that will be RC to the power of K minus 1 over K RC minus 1. Yeah. So this is the efficiency that you get from thermodynamics. And we won't discuss about this more in detail because you have learned about that. So this is just a review of what you have learned. Now, what is the compression ratio? So we have seen before that compression ratio is the maximum over the minimum, yeah, volume. Now, what about the cutoff ratio? Still remember? What is the cutoff ratio in diesel cycle?
Ma'am.
Yes.
Cutoff ratio is ratio of volume when it's expand and compress, ma'am.
Yeah. So when we have the diesel cycle, we will see about this. We will see about this again later. Yeah. So we will have a compression process. Yeah. Compression process, and then we have a iso pressure. Yeah. Isobaric isobaric power process. Yeah. And then we will have the expansion here and this one. So this is heat addition. Yeah. Sorry, heat addition or power process. Yeah, heat addition. Okay. So when we have this one, so that will be the ratio, yeah, the ratio between this volume. So what is this? Phi, this is 1, 2, 3, and 4, yeah. So that we have phi 2 and we have phi 3, yeah. So cutoff ratio is, what is cutoff ratio?
V3 over V2 maybe.
Yeah, phi3 over phi2. So that is the cutoff ratio. Yeah, because it's not occurring in the isochoric. Yeah, so heat addition is not performed in isochoric process, but instead in isobaric process. It means that during heat addition, during combustion, we have an increase of volume there. Yeah, so that will be the cutoff ratio. All right. Yeah, so that is correct. Yeah. Okay, so this is the efficiency. So this will be the thermodynamics or the theoretical efficiency. So this will be used in front, yeah, as we have seen in the front slide before, that this will determine, that will be used as well to find the indicated power, yeah. So the thermodynamic cycle here will be the indicated power. Okay, so you have learned about this and you can use these equations, yeah. So that here, when we have that value, yeah, uh, we can find here as a ratio as well. Yeah, this is what we've seen in the energy level as before. Yeah, in the diagram, in which when we have the indicated thermal efficiency, this is the ratio of the indicated work to the heat consumed during the same time. So the heat consumed is the fuel power. Yeah, so this is actually the fuel power, or this is what we have discussed before. Yeah, so this is P fuel. Okay, and if we have these equations, yeah, sometimes you see this equation. So this means that this is defined for a certain, yeah, for a certain unit. So be careful with this. So this is constant for certain unit, for specific unit. Yeah, so this is usually in British. So if you have that in British, so then usually you multiply with this. But I would suggest you just doing the regular way. Yeah? Try to convert the unit manually. Yeah. So this is to reduce the error during the calculation. And mechanical efficiency, as what we have seen before, is the ratio between brake horsepower and to the indicated horsepower. Yeah, or shown as this one. And the brake thermal efficiency, yeah. So the brake thermal efficiency is also called the overall, yeah, as what we've seen before. So that will be, yeah, the brake horsepower over the total power, yeah, from the fuel. Okay. And if we have this relation, yeah, we know that this will be a multiplication of the efficiency. So the total efficiency will be the multiplication of the thermal indicated efficiency with the mechanical efficiency. Yeah. And we have also the combustion efficiency, in which combustion efficiency here dealing with the ratio of heat generated to the heat value of fuel. Yeah. In which here we have Q generated over HV. Yeah, so this is the term which is often used in the combustion process. Now, when we talk about performance, yeah, so there are lots of performance that can be used. That can be, there can be many parameters, yeah, that can be used to define the performance of the internal combustion engine. So another performance is the charge efficiency. Yeah, charge efficiency. So what is charge efficiency? Here is the ratio of the weight of the actual fresh charge. So fresh charge here means air. Yeah, charge here is the air that goes into the piston. Yeah, so charge here is the air that goes into the piston. So when we want to calculate charge efficiency, is the actual weight of the air. Yeah, the actual weight of the air that is sucked in the process. Yeah, sucked in the piston during the process, over the actual weight that can be provided in the piston. Yeah, so this is dealing with the volume of the piston. So if we want to find the actual weight of the air inside the piston, so that will be the volume Yeah, so that will be the volume, and here is the displacement volume. Yeah, so that will be the displacement volume. Yeah, multiplied by the density of the air. So this will be the weight. Yeah, so this will be the weight that goes inside the cylinder during the process. Yeah. So we see here that we have charge efficiency. So what is this? What this means? Yeah. So this means that actually the air is not filling all the volume. Yeah, as what it is in ideal case. So usually the air that goes into the combustion, the cylinder, yeah, is less, yeah, is less than the capacity, yeah, the weight capacity of the cylinder. So this is called charge efficiency. Yeah, in which we can find the density, yeah, based on the gas ideal gas relation. Yeah, so the density will be the pressure divided by R, which is a constant for constant gas constant. Yeah, and we have T is a temperature of the air. Now, aside from charge efficiency, we also have the terms of volumetric efficiency. Yeah, volumetric efficiency. So volumetric efficiency, yeah, almost similar to charge efficiency, in which now we calculate based on, yeah, similarly, yeah, the volume. Yeah, so charge efficiency is based on the volume. So more or less similar, yeah, with charge efficiency. Sometimes it's said to be charge efficiency or uh, volumetric efficiency. Yeah, so more or less similar. So because of the cycle occur in the short time, yeah, and there will be a time needed to open and to fully open and close the valve, yeah, of the intake, so that this will restrict the amount of air that goes into the cylinder. Yeah, because there is a delay. Yeah, when we open the valve, it's not possible to open it very fast, so, while the process itself is very fast, so that not all of the volume can be filled with fresh charge. Now, that other performance parameter, yeah, so this is still mixed in Indonesia. Yeah, so we have the term of fuel air ratio, or sometimes we have the terms of air fuel ratio. So it's similar. Yeah, which one do you use? Yeah, usually it's more common to use the term of fuel air ratio, in which this is the ratio. Yeah, the ratio between the fuel and the air. Yeah, and what is used is the mass. Yeah, the mass of the fuel over the mass of the air. Okay, and when we talk about combustion process, so that we have stoichiometry. What is stoichiometric process? So that we have stoichiometric combustion process here. So it's dealing with the perfect combustion. Still remember? Yeah, so this is dealing with the perfect combustion. So when we have stoichiometric, so this is based on the chemical composition. Yeah. So the reaction here will be based on the chemical composition of the fuel. Yeah. So then when we talk about a stoichiometric process, it means that we have to understand the chemical composition of the fuel. And based on that, we can calculate how much oxygen, yeah, later how much air is needed to get the perfect combustion. Yeah. So means that we have the stoichiometric process. Now, sometimes the air that is provided in the cylinder, yeah, is not exactly the same as what we have in the stoichiometric process. Yeah. So when we give more air, yeah, more air compared to what it should be in the stoichiometric process, yeah, if we give more air, compared to the stoichiometric process, so it means that we have the lean mixture. Yeah, it means that we have more air than it should be. So then we have a lean mixture. Yeah. When we have air less than what it should be in the stoichiometric process, it means that we have rich mix. So then when we talk about rich or lean, what we see is the composition between the fuel and the air. Yeah, more fuel, it means that it's rich. Yeah, more fuel than the air than what it should be in the stoichiometric process, it means it's rich. Yeah, while if we have more air, it means that we have lean. So that here we also have the relative fuel air ratio. Yeah, the relative fuel air ratio, in which this is the fuel, the actual, yeah, the actual fuel air ratio compared to the stoichiometric one. Yeah. So this is said to be the relative fuel air ratio. Yeah. Yeah. Okay. And later we will see about this. Yeah. We will see what is commonly used. Yeah. For example, in the gasoline engine. Yeah, so it's usually not exactly one. Yeah, if we give one for relative fuel air ratio, it means that the actual air that we give is is similar to what is required in the stoichiometric process. Yeah, but usually not like that. So we will see later. Yeah. And this one as well also for diesel engine or diesel cycle. Yeah. So usually we don't use exactly one, but yeah, depends on what we need. Yeah, from the for the application. But commonly we apply lean mixture. Yeah, lean mixture. Particularly if what we want is a more green or low cost. Yeah. So this is dealing with how we give the fuel air ratio. Okay, so we have discussed of that, yeah, several parameters that are important. Any questions up to here?
With me, ma'am.
Yes, William?
I want to ask in the charge efficiency. Does it
Mhm.
mean that we measure it when the piston reach the bottom dead center position? Because
Which
it
one is that?
contains the volume.
All right. This one?
Not, ma'am. After this charge efficiency.
The efficiency chart. Which one is that?
After this. Yeah, this one. This one, ma'am.
Oh, the volumetric, yeah.
No. Before it.
The
Before this.
charge efficiency.
Yes, charge.
Oh yeah, yeah. We calculated that based on uh, the real flow rate of the air. Yeah, so we can measure the flow rate of the air. Yeah, so we can measure so that we can find the weight. Yeah, yeah. So this is based on, yeah, usually this is taken for uh, during some time. Yeah, usually it's taken during some time. Yeah. And then afterwards, so not only it's quite difficult. Yeah, it's quite difficult to it's quite difficult to get the weight only for one stroke, for example. Yeah. So in actual case, usually we measure it for some time period and then we find the average like that. Yeah. Yeah, because it's quite difficult to get only one stroke. Yeah, when it's in real case, because it's very fast. Yeah, so it's difficult to get only for one cycle. So what we do is that we measure the flow rate. Yeah, we measure the flow rate and take it for a certain period. Yeah, and then we divide it with the number of cycle that is performed. Yeah, while this one can be calculated. Yeah, based on the dimension of the cylinder. Yeah. Yeah, so I think that will be the answer. Yeah.
Okay, ma'am. So it's lebih ke hubungan ke flow rate ya, ma'am?
Ya, ya. Jadi
That's the way.
biasanya seperti itu ya. Jadi sulit ya kita mengukur biasanya berapa udaranya ya real biasanya dari flow rate-nya. Ya, flow rate-nya itu yang bisa terukur.
Okay, ma'am. Thank you.
Okay. Any other question?
Excuse me, ma'am.
Yeah, Sultan.
I want to ask about the heating value. How could we calculate that heating value? Are we should do the stoichiometric first, or it just using the thermodynamic law about the internal energy?
Can you repeat the question?
How to calculate heating value, ma'am?
Heating value is not calculated. Yeah, so it depends on. Usually we test it. Yeah, so there is a test for the chemical composition inside. For example, we have coal. Yeah, we have low rank coal and we have high rank coal. Yeah, so even a coal can have many chemical composition inside, and that will determine the heating value. Yeah, so that will determine the heating value. So that there will be a test. Yeah, so chemically tested of what are the composition and what will be the heating value. Yeah.
Okay, ma'am. So heating value is empirical variable, right, ma'am?
Yeah. I would say like that. Yeah. So we have to do testing on that. Yeah. So testing for the material for the fuel that we have. Yeah. Correct.
Okay, ma'am. Thank you, ma'am. Clear enough,
Yeah.
ma'am. Thank you.
Yeah. Okay. Any other question? All right. If there is no question, so we will continue. Yeah, so this is dealing with heating value, what you asked, yeah, before. We'll check that. Yeah. So heating value is the energy released in a perfect combustion on a unit of fuel mass. Yeah. So if we have a 1 kilogram of fuel, for example, and how much kilojoule provided there. Yeah. And when we talk about heating value, there are two types of heating value. So we have the higher heating value. So this should be higher, yeah, higher heating value, and also the lower heating value. So this is actually almost similar, but depends on which value that we use. Yeah. Sometimes it's more common to use lower heating value. Yeah, it depends. Yeah, you can use any. But what is the difference? Yeah, the difference is that how the heating value is calculated. Yeah, so this is the difference. So when we have the higher heating value, so that when this value is obtained as the amount of heat released by a specific quantity, in which this will be a unit of fuel mass, which is initially at 25 degrees Celsius. Yeah, so the fuel is at 25 degrees Celsius. And once it is combusted, and then the product have returned to a temperature of 25 degrees Celsius. Yeah, so that means there is a combustion process, and then it returns to a low temperature again. Yeah, so this means that this calculation will include the latent heat of vaporization of water in the combustion product. Yeah. Okay, so there should be an addition of the latent heat here of the water. Yeah, the latent heat of vaporization of water. Well, if we have the lower heating value, this is lower because the value will be lower than the higher heating value. Yeah. What is obtained here is this is the amount of heat released by combusting a specified quantity of fuel, which is initially 25 degrees Celsius, so this is similar, and returning the temperature of the combustion product to 150 degrees Celsius. Yeah, so it means that it's already higher than the vaporization temperature of the water, so that here it assumes that the latent heat of vaporization is not included in the calculation. Yeah, it's not included in the value. So that's why this value has a lower value compared to this one. Yeah, so this is the difference. But actually, yeah, you can do the calculation using high heating value or low heating value. That's fine, but you should mention it, yeah, with which value that you use in the calculation. Yeah, so that will be both will be okay, and this value both are provided. Yeah, if we cannot do the testing by ourselves for the fuel that we have, so we can use widely available data. Yeah, so you can googling it, for example, finding for a certain fuel, for example. Yeah, although this not be very accurate sometimes. Yeah, so because it can be very large. Yeah, but at least you know the range of the heating value. Yeah, so you can find this data as well. Yeah. And heating value here, because it contains energy, yeah, it's sometimes said to be calorific value. Yeah, so this is the other name, calorific value. So how much calorie, yeah, or the heat energy content. All right, so that back again to spark ignition engine. Now we already discussed several parameters, yeah, regarding the power, efficiency, the volumetric efficiency as well, and also fuel air ratio. Now we will go in more detail in spark ignition engine, and why we need to go here first, because we will talk about pressure. And when we talk about pressure, again, we will use the PV diagram. Yeah, it's very related to the PV diagram, and we know that the process between the Otto cycle and the diesel cycle is slightly different, yeah, for the PV diagram, as what we've seen before. So that again, for spark ignition engine, we can have two types of engine. We have 4-stroke and 2-stroke. Yeah. So I think what we've seen before is already 4-stroke, and I will not repeat this. Yeah. We have 4 processes. We have the intake process. We have the compression process. So this is the first stroke going down. The second stroke going up is compression. And then the third stroke is the power process, yeah, or expansion, yeah, when the spark plug fire. And then the last stroke is when we pushes the exhaust gas out through the exhaust valve. Yeah. So a total of 4 stroke for one cycle. Yeah, 4 stroke for one cycle. Well, if we have 2-stroke engine, yeah, when we have 2-stroke engine, it means that here we need only 2 stroke or 2 movement, yeah, 2 step of movement for the piston, for the head of the piston. Yeah. So that here we have the fuel air inlet port here, yeah, in which it will take the fresh air and the fuel, the mixture from the carburetor, goes in, yeah, when it goes up, yeah. So we have the compression and intake, yeah. And then when it goes down, we have the power and then the exhaust in one step or one stroke. So a total will be only 2 stroke, yeah, only 2 stroke or 2 movement up and down for the complete cycle, in which the cycle will remain the same, which is 4 processes in a cycle. And we see here that because it has slightly different configuration, yeah, so that we have the shape is also slightly different, yeah. We see here that we have the fuel inlet port and exhaust port, in which this is not connected to a valve as before, yeah. So we have a port, yeah, but we don't have the valve which regulates here, yeah. Okay. And perhaps you want to mention what are the difference between 2-stroke and 4-stroke? What do you think of the two when you compare that? What is it different?
Maybe,
Yeah.
maybe from the acceleration and torque, ma'am.
Okay. What do you think?
If I observe when I observed before, 2-stroke engine will have the higher initial acceleration than the 4-stroke engine. But for the top speed and for the top speed, 4-stroke engine will have greater top speed than 2-stroke. Maybe like that.
Yeah. Okay. Yeah. Yeah. So that is one thing. Yeah. About the performance difference. Yeah. So that is correct. Yeah. Why the acceleration is faster in 2-stroke engine?
Maybe because in two-stroke each one up and down process it generating power than the first stroke because first stroke in each two up and down process it will generate just one power.
Yeah, correct. Yeah. So if we look at here, yeah, it means that for one cycle, one rotation, it's already producing a power. So power is produced every rotation. Yeah, every rotation, a single rotation here will create power. While in four-stroke engine, it means that you need two rotation, two revolution here, yeah, in order to get the power. So of course, yeah, based on that, yeah, the acceleration will be higher, yeah, because the power already control the revolution in every step of the revolution, yeah. Okay, so that is one thing. And what about the configuration here? Dealing with this, sometimes we notice there is a difference as well between two-stroke and four-stroke engine. What about the exhaust gas?
For the exhaust gas, I think the emission is much worse in two-stroke because, as we can see, in the combustion, two-stroke engine burns their oil, as opposed to the four-stroke where the oil is the oil cannot enter the combustion chamber.
Yeah. Yeah, so that is correct as well. Yeah. So because of this configuration, because of the shape, because of the because of the air goes into the lower side here, it means that the air will be everywhere. Yeah. And when we look at the piston here, when it moves down and up like this one, so it means that it will need lubrication as well. So we have oil, yeah, to support there, to supply there. And of course, this oil will mix with air, and therefore, when it's burnt, the oil will be burnt as well. Yeah. So therefore, you need to provide oil, yeah, give sufficient oil every time. And you notice that there will be white smokes, yeah. So this is the oil that is burned, yeah, because of this configuration. Yeah, so that is correct. Any other? All right. So perhaps you know this better than me, yeah. All right. So we will continue now, yeah. And also here, if we look at if we look at the process here, yeah. So yeah, in two-stroke engine, we can see here that this is the first process, the first stroke, which is induction or intake, yeah, and then compression when it moves up, and then when it moves down, yeah, when it moves down here. So we have here the port is open, and sometimes it's not really easy to isolate this effect. Yeah, it means that uh, yeah, there might be unburned fuel which is released to the exhaust port. Yeah, because we see here there is a slight mixture here, although we want it to be like sort of flushing, but sometimes the fresh fuel and air mixture here may mix up, and some part may goes out to the exhaust port. Yeah, so yeah, when we talk about the efficiency of the fuel, specific fuel consumption, we will discuss what is that before, what is specific fuel consumption after this. But we can logically think that when we look at this diagram, when we look at this figure, yeah, we can think that the four-stroke engine will have a lower specific fuel consumption. Yeah. So in terms of fuel consumption, the four-stroke engine will be better compared to the two-stroke engine. Right. So this is the Otto cycle, yeah, in which this is the ideal one, yeah. And you have learned about this as well, yeah. We have the first step here, which is the first stroke, yeah. And the first stroke here is the intake, yeah, the intake. And then from 1 to 2 here is the compression, so it moves up and then it compress the air. the mixture of air and fuel. And then we have heat addition here. So in Otto cycle, yeah, the main difference in Otto and diesel cycle is the heat addition process. Yeah, the heat addition process. And I think you have learned about this. Yeah, so we just do the review here. So the heat addition process is performed in an isochoric condition, which is at very close at the top dead center. Yeah, very close to at the top dead center. So that we can assume this that to be isochoric. And afterwards, we will have the expansion process in which this will have greater volume expanded, yeah, from 3 to 4. And this is, in ideal case, this is said to be adiabatic reversible process, or we can say that to be what process here? Adiabatic reversible?
Entropic.
Correct, yeah. So this to be isentropic process in ideal case, yeah. So that we will have isentropic expansion. And then afterward here we have heat release, yeah. We will have heat release. And then we go, we pushes the exhaust gas up, yeah. Okay, so this is the theoretical Otto cycle and how it looks like in the actual case, yeah. So this is the actual case. So there will be a difference between the dashed line here. So the dashed line here is the theoretical one, and the actual will be shown by this line, yeah. So we see here that, yeah, there is a change in pressure as well during the exhaust and intake process. And then the real compression process is not following the isentropic. Yeah, so there will be a bit of different. And there is a bit of different and on when we want to start firing, yeah, the spark plug. When we start to ignite the spark plugs. So the ignition is not performed here at the top dead center. Yeah. So it's not when it reaches the maximum point and then we started to ignite it, but not before that. Yeah. So we notice here that before that we already ignite the spark plug. Yeah. So this is a spark plug ignition. So here we see here that at this point, yeah. So not reaching the top dead center. So this should be the top dead center. And this will be the bottom dead center. So we notice here that in actual case, before it reaches the top dead center, we already ignite the spark plug. And afterward, it will be burnt. Yeah, we have a heat addition here, which is a burning process of the fuel. And then afterward, we have the, we will have the expansion process here. Yeah, and we see here that in actual case, of course, there are losses so that the highest pressure cannot be as what we expected in the ideal case. Yeah. All right. So when we look at this graph, yeah, again, we can draw the stages of combustion in this diagram. Yeah, in which this is a pressure to the crank angle. So if you're interested in this, you can further take the elective course, yeah, motor pembakaran dalam, internal combustion engine, yeah. So if you're interested in this, you can take further the elective course motor pembakaran dalam. Perhaps Pak Ato now, yeah, Pak Ato or Pak Bambang Sudarmanta, yeah. Right. So what happens here? Yeah, we notice that we have the spark plug ignite before. So why we need to do that? Now we will see the process, the actual combustion process, combustion stages in the gasoline engine. Yeah. So we see here that we have the crank angle. So if you imagine the crank angle here is the position, yeah, the position of the connecting rod to the crankshaft, yeah. And when we have a zero crank angle, it means that it will be at the top dead center. Yeah, when we have 0 degree, it means that the position of the piston will be at the maximum point, which is at top dead center. And if we have 180 degree, yeah, it means that it is, so 0 here means that is at the top here. When we have the position is here, yeah, the connecting rod is at position 180. So this is 0 degree and this is 180 degree. It means that it will be at the bottom dead center. Yeah, so we have top dead center and bottom dead center. So when we have 0, it means at the highest highest position, yeah, at top dead center. So we will see here that if, for example, if for example, we just do the movement of the piston, so we know that because of compression and expansion process, yeah, without any combustion, there will be an increase and decrease of pressure, yeah, increase and decrease of pressure. But now we add heat addition, we add combustion process. So what we perform here, when we do compression, so it's compressed, so the pressure increase, yeah, up to A, and then A here, yeah, we start to ignite the spark plug. Yeah, so we ignite the spark plug. Yeah, and afterwards, what happens after we ignite the spark plug? Yeah, it means we start. We start the. Actually, we want to start the combustion process, but what happens? It's not directly combusted. It's not directly fired. Yeah, so the fuel is not fired yet here. So not automatically fired, but we need some time. So this is called the ignition lag. So there is a lag or a delay. Yeah, although we already start the fire. Yeah, we already start the fire. For example, the battery is already turned this on in here, but the fire process is not occurred yet. So we have an ignition lag. We have a lag. Yeah, up to B. Yeah, and then after B, now it start to fire. Yeah, so then afterwards we have a propagation of flame. Yeah, so we have the wave of the flame, so that this will increase the pressure very sharply. Yeah, increasing the pressure very sharply up to C, and then afterward this will be the maximum pressure. Yeah, and afterward it will have of afterburning process here. Yeah, afterburning. So here is the maximum pressure, and then afterward we have afterburning. So this will be the expansion process. Yeah. So this is the stages in combustion. So therefore, because we look at the combustion stages in here, we know that we cannot ignite it at the top dead center because we will late. We will be late, yeah, because there is always a lag or a delay when we start a fire. Yeah, there will be a lag. So that we have to start to fire it. We have to start to ignite the spark plug before it reaches the top dead center. So we will look here at the explanation. So point A here is spark ignition. Yeah, so this is the mix up. Yeah, spark ignition at about 28 degrees before top dead center. Yeah, so this is not always. You see, in this case, it's less than 20, so probably 18. So this is really depends on the engine. Yeah, the engine size and so on. So spark ignite several degrees before top dead center, and then the pressure increase detected, which is about 8 degrees before top dead center. So we see here, we have a sharp increase here. It means that we start the propagation of flame. And then point C is the maximum pressure increase. So we go back here. C is maximum pressure. And then afterward, T, yeah, will be the area, yeah, in which that will be the afterburning region. Yeah. So if we look between stage A and B, here we have the ignition lag is actually the preparation stage, yeah, or usually we say ignition or delay of the combustion. And what may affect this ignition lag, yeah, is it close enough? Yeah, is it 28 degree or 18 degree or 15? Yeah, how can we make it suitable for this delay phase? It depends on chemical processes. Yeah, so it depends on the chemical process, which depends on the fuel properties. Yeah, so we see here what affect this. It can be the fuel properties. It can be the temperature. Yeah, the temperature of the air. Yeah, and the pressure of the air as well. The exhaust gas proportion. Yeah, for example, the composition of the exhaust gas. Yeah, for example, if you have nitrogen oxide and so on, yeah, and other factors. So this depends on how much time that is needed in the ignition lag. And after it reach, after the ignition lag, yeah, and then when the fire starts, then we have the propagation of flame. So this is in the kind of wave, yeah, the fire wave. So there is a wave to other area. So, so the burning process will start from the area close to the spark plug, and then it will the wave will propagate to all area, yeah, surrounding in the cylinder. So because this is dealing with wave, so this is a pure and simple mechanical process, and this shows the start of the second stage, which is indicated by the sharp pressure increase. Okay, so these are the combustion stages in gasoline engine. Okay, now when we talk about fuel properties here, yeah, and also about the stoichiometric, so we have to look at this, yeah. So how to find how to find the reaction, yeah, to define the reaction process for a fuel. So for example, here we want to calculate the requirement, yeah, for a fuel. For example, we have CmHn here, and this depends on the fuel, yeah, on the fuel. So for example, we have isooctane, so that will be 8, yeah, C8H18 plus, in order to make it be able to, for a perfect combustion, so we need to find the proportion, yeah, or the proportion or the composition of the oxygen needed in the combustion process. Yeah, so that if we have CmHn plus O2, yeah, oxygen, that will be a product of carbon dioxide and water vapor, yeah, H2O. So that here, when we want to make it the same, yeah, so C is M, so of course this is M, and H here is N, because this is H2, so this should be N over 2, so that the oxygen needed will be equals to the value, yeah, the coefficient on the right side here, so that the oxygen needed will be M plus N over 4, yeah. So that if you have C8H18, so that we have M is 8, and H is 18, so that 18 divided by 4 is 4.5 plus 8, so that will be 12.5 of O2, and that will react and give a product of 8 of carbon dioxide and 9 of water vapor. Yeah, and if this is oxygen only, if we talk about air, yeah, if we talk about air, so that this will consist of nitrogen, yeah, so about 80% of air is nitrogen, so that we can write it down as air here as O2, yeah, plus 3.76 nitrogen. So that with this, so we have the value. Now, based on this stoichiometric reaction, yeah, based on this stoichiometric reaction, so that we can calculate the fuel air ratio for the stoichiometric process. Yeah, so the fuel air ratio for the stoichiometric process will be 8. This is the fuel, yeah, so this one is the fuel. So we have 8 times C, yeah, so C here, the mass of C is 12. So 8 times 12 plus 18 times hydrogen is 1, yeah. Over, we have the air requirement here is here, yeah, in which O2, so O2, O is 16, so times 2 is 32. So times 12.5 plus 12.5 times here, the coefficient, which is 3.76 times nitrogen is 14, so N2 is 28, yeah. So when we calculate the mass required here in the process, yeah, to the mass of the air, so we will have the fuel air ratio become 0.0664. So this is for a fuel which is pure isooctane, yeah, pure isooctane fuel. What about the air fuel ratio? It will be the same, yeah. We just divide the air with the fuel mass, or that we can say that air fuel ratio will be 1 over fuel air ratio. Yeah, so 1 divided by 0.0664, that will be 15.05. So this is the stoichiometric, fuel air ratio. And as we've seen before, we can have the relative fuel air ratio. It means that we don't always necessary to provide the exact value as this one. Yeah, we can provide lean mixture, or rich mixture, depend on what we need. Yeah. Okay. So when we see here that when we want to in actual case, what is the air supply that is given? So usually we use the excess air, or we say that it's more common to use lean mixture. And what is the composition? Usually for this gasoline engine, it can be lower than that, 0.95. So this is a bit rich, rich mixture, up to 1.1. Yeah. So this is the excess air. If we have 1.1, it means that we give excess air 10% higher than what is needed in the stoichiometric condition. Yeah. So this is the excess air. While diesel engine usually more even leaner for diesel engine, we use 1.1 up to 1.4. Yeah. So if we use 1.4 here, it means that we give excess air, which is 40% higher than the stoichiometric one. Yeah. Okay. Okay. Any question?
I would like to ask, ma'am, why in practice we need excess air, ma'am, in real life?
Yeah. Why we need usually more excess air? Yeah, it's dealing with several factors, including the efficiency of the volumetric efficiency or the charge efficiency. Yeah. So usually we provide more. Yeah. Because sometimes, what that the air, the actual air that can goes into the cylinder, it's not as much as what we desire. Yeah. So therefore we have to give more than that. Yeah. And also usually dealing with the temperature. Yeah, dealing with the temperature. So when we give the stoichiometric exactly to the stoichiometric, so it means that the temperature will be higher. Yeah, the temperature will be higher. So this is one thing to consider as well. So usually we give more air, so that the temperature will be reduced. Yeah, and also sometimes in the combustion process, because of the efficiency of the combustion itself, sometimes there are unburnt fuel. Yeah, unburnt fuel. So it is expected that giving more fuel, giving more air, can reduce the unburnt combustion process. Yeah, the unburnt fuel. Yeah, can reducing the unburnt fuel. Yeah, so that is the reason. Yeah, because we have several delay, for example, in the combustion process. Yeah, so sometimes not all of the fuel is burnt. So that if we give more air, if we give more air, it is expected that all of the fuel inside can be burnt. Yeah, can be burnt like that. So this is another reason. Yeah. Okay, so is that answering your question, Fifi?
Yes, I think so, ma'am. Thank you, ma'am.
Okay. Yeah. All right. Any other question?
Ma'am,
Yes.
I would like to ask about excess air for auto engine. On your PowerPoint, it's mentioned that there is 0.95. It's mean less than the stoichiometric condition, right, ma'am? So what the reason of it?
Yeah. Yeah. So this one, yeah. It really depends on what we need. Yeah. Sometimes sometimes we need a more powerful engine. Yeah. Sometimes we need a more powerful engine. So if yeah, I think it's yeah, in more powerful engine we can make it richer. Yeah, means more fuel, in which we what we want is to have a very high torque. Yeah, usually like that. Yeah, so we can increase that. Yeah, but normally uh it's more in lean mixture compared to rich. Yeah, although this is possible, we will see later that there is a limit. Yeah, there is a limit for this mixture, whether rich or lean. We cannot be too rich or too lean. Yeah, if it's too lean, so there will be no combustion at all. Too much air and very little fuel. Yeah, so it cannot be burned. Also, if we have too much fuel, yeah, and less air, it will not be burned as well. Yeah, so there is a range. Yeah, and in this case for 0.95, this is still used in quite uh, it's quite common. Yeah, in this case it's quite common, and this is really depends on what the function of the engine. Yeah, sometimes, for example, if we have a car and we need high torque, for example, yeah, we can start, for example, the power mode, yeah, and so on. Yeah, so this is to controlling that we reducing the air that goes into the piston, yeah, in order to get a higher torque. Yeah, but of course this will be require more fuel. Yeah, and on the other side we will see that it will have higher specific fuel consumption, which is commonly not a good idea. Yeah, because what we want is usually low cost, greener engine and so on. Yeah, so yeah, but really depends on our needs, yeah, of the engine. All right. Any other question?
Thank you, ma'am, for the answer, ma'am. Excuse me, ma'am, you still mute your microphone.
Yeah, sorry. Yeah, so we have the limit here in which this is the practical limit. Yeah, so this is the practical limit for, yeah, this is for the fuel air ratio. Yeah, so this is the air fuel ratio. Yeah, back again here. We have air fuel ratio, which is about 15.05. Yeah, so here, yeah, this is really depends on the fuel. Yeah, but generally we have this stoichiometric in about 14.5 or about 15. Yeah, and what is possible, we have the practical limit in which this is from 9 up to 20. Yeah, so this is for the air fuel ratio. If it's too high, and this is the ignition limit. Yeah, this is the ignition limit and this is the practical limit. So here, what if you have the air fuel ratio less than 9? It's still possible. Yeah, it's still possible, but it's not practical anymore. And also here, yeah, we can still burn this on, but yeah, it's not practical. And then too lean or too rich, we cannot burn it. Yeah. Right. So practically, the air fuel ratio is around around 9 to 20, which is in the practical limit. Yeah, usually around this value. Okay, so that if we look at the performance of the spark ignition engine or the gasoline engine. So this is generally the performance chart, yeah, in which here we have at the bottom here is the speed, yeah. So we have the rotational speed, and we have on the left here we have the vertical, or the ordinate here is the horsepower. So this is the power, and also we have the BMEP. We haven't discussed about that, but you might have learned that in thermodynamics. And we have torque, and we have PSFC on the right, yeah, in which this is generally how the performance chart look like, yeah. So we have the power, in which the power is increasing, and then it will reach the peak power, and then it will reduce, yeah. Again, similar to brake horsepower, yeah. And what about the torque? Yeah, similar. Yeah, it will increase, and then it will reach the maximum, and it will be go down. And then we have the BMEP, which is, what is the BMEP stand for? BMEP. What is BMEP?
Brake mean effective pressure.
Yes, correct. Yeah. So BMEP is brake mean effective pressure. So what does that mean? BMEP?
The average pressure pushing the piston down, I think.
Yeah. So average pressure, but mean effective pressure. Yeah. So it's average, but it's not like finding the average between the two pressure. Yeah. But what we use as BMEP is the pressure in which the area underneath that pressure will be, that will be the work. Yeah, that will be the work. So the work, so this pressure is calculated from the work of the cycle. Yeah, so we will see the illustration of that. Yeah, I think you have done that as well. Yeah, and here we have friction horsepower. So we have the line here, which is friction horsepower, and we have the value here is increasing. So when we have a rotational speed getting higher and higher, of course the friction will be higher. Yeah. So when the revolution is higher, it means that the movement of the head of the piston will be faster as well, so that the friction power will be higher as well. And we have PSFC, which is PSFC here stands for brake specific fuel consumption. And we can see here that this graph for PSFC is going down and then going up again. So we can see here that we have a value, a minimum value for PSFC. So it means that if we want to have the lowest fuel consumption as much as possible, the lowest one will be at this point. Yeah. So for example, if you're driving a car and you want to have the minimum cost for the fuel, yeah. So try to operate the engine at this rotational speed. So not too high, yeah, but not too low. Yeah. If you get this optimum, so you get the lowest cost for the fuel. Yeah. Okay. So we will discuss one by one here. Yeah. We have the torque mentioned here. Yeah. We have the brake torque. So how do we calculate the torque? Yeah, so we can use this by a brake here, yeah, a dynamometer, like a brake like this one. So if we have a rotor or a shaft that is rotating, so we put on stator, and then we measure the force by, for example, here using the load cell. Yeah, so that here we can calculate the torque, which is given by this shaft. Yeah, so the torque will be F, the force, times the distance. Yeah, the distance, or the elbow. Yeah, the elbow, like this one. So that the power. So when we have this one, we can calculate the power. So that this power will be torque times the rotational speed. Yeah, in which omega here means in radial per second. So if we have n, so that omega here is equal to 2 pi n. And here is the revolution, yeah, revolution per second. Or if we have per minute, so that will be 2 pi n over 60. Yeah, so in general, the power here will be torque times omega. So what power is this? So what power is this? We have several types of power before. We have fuel power, we have indicated power, and we have brake power. So what is the power here measured by the torque?
I think it is
Brake power.
brake power.
Yes, correct. So this is brake power, yeah? Because this is what we obtain in the shaft. So it means that this is a useful torque, yeah? So this will be the useful power. Yeah, so this is the brake power. So this is how to measure the brake power. Yeah, so you can perform this. For example, if you are doing a final exam, yeah, in internal combustion engine, we have that. So you can measure the torque, yeah. And also here, we have the indicated horsepower. So back again here, we have brake horsepower. So we understand how to measure it, yeah. So brake horsepower should be measured, yeah. Brake horsepower should be measured. And then we have indicated power or indicated work. Yeah, so before we talk about power, so we talk about work first. So what is indicated work? It's actually based on the thermodynamic cycle. Yeah. So for example, we have a cylinder pressure data like this one. Yeah. So that based on this, we can calculate the work. Yeah. We can calculate the work. So the work is the integration of PdV. Yeah. The integration of PdV. Or we can say that the work is actually here is the area. Yeah, we can say that to be the area of the cycle. Yeah. In which here we have the area which is greater than 0 is positive. It means that it's producing the work. But also during the intake and the exhaust process, we need the work. Yeah, we need the work. We need the work to drive that. So it means that there is a negative work. So there is a work inside the system, yeah, during this process. Okay, so we have positive and negative, so that the total work here, the net work here will be the indicative. So we can see this from thermodynamic cycle. Okay, so that if we want to find the thermodynamic side, we want to find the power. Yeah. So say if we are able to calculate the indicated work, which is from the cycle. Yeah. So if we can find the integration of the area and we have the indicated power, the indicated work, so then we can find the indicated power. Yeah. So this is the indicated work. Yeah. Which is from the diagram. Yeah. From the PV diagram, we have the indicated work. And then we multiply it with the crankshaft speed. Yeah. How many revolution per second? So that we will have the power. Power is in second. Yeah, in second, per second. So it means that how many revolution per second? Because this will multiply the work that is obtained. Yeah. So for example, if I have 60 revolution per hour, per second, yeah, 60 revolution per second, for example, for various, this is not for an engine, yeah, engine usually 2,000, 3,000, yeah. Yeah, so say we have a certain revolution per second. So that now we have to divide by NR here, which is the number of crank revolution per cycle. So if we have 4-stroke, because 4-stroke means that every 2 cycle producing 1 power, it means that it should be divided by 2. Yeah, because it means that this work is not generated every revolution. Yeah, so this work is generated every number of revolution divided by 2. Yeah, because it requires 2 revolution to produce 1 work. So that we have to divide it by 2 here if we have 4-stroke engine. But if we use 2-stroke engine, it means that every cycle, every revolution will produce work. So that here NR is equals to 1. It means that we don't have to divide it. So the power, the total power will be the work for a cycle times the number of revolution. Yeah. So understand the concept here. Yeah. All right. So why we need to divide it with this one? Because this shows when the work is produced, whether it's every revolution or every 2 revolution. Yeah. Okay. So this will be the indicated power. Yeah. This will be the indicated power. Okay. So we understand now that brake horsepower is measured, indicated, can be calculated. Yeah. So that now because we can calculate this one, so that we can imagine how to increase the power. Yeah. So how to increase the power? So when we look at here, yeah, when you look at here, when we want to increase the power, so what we can do is that we want to make this area larger. Yeah. So one thing to do it is to increasing the compression ratio. Yeah, increasing the compression ratio. Also increasing the engine size, of course. If we increasing the engine size, it means that for every cycle, it will be more powerful. Yeah. So of course, we can increase the bore diameter. So therefore, if you, for example, have a car, for example, 2000 cc compared to the LGCC one, which is 1000 cc, of course, you can see the difference in the power. Yeah. So the engine size really depends the power that can be produced. Yeah. Yeah. Wait a moment. Right. And last is by increasing the engine speed. Yeah. So if we can increase the engine speed, yeah, it means that we're increasing this one. Yeah. Of course, when we're increasing N, so the power will increase as well. Yeah. So there are 3 ways to increase the power of an engine: the engine size, the compression ratio, and the engine speed. Okay. So that if you look at power and brake, yeah. So we can see this one, yeah. Yeah, I think it's Azan. We take a break for 2 minutes, yeah, and we will return. 2 minutes break. Yeah, okay. We will continue here in the power and torque diagram in more detail. Yeah. We will see why this performance is shown by this curve. Yeah, so we have a low and a maximum and goes down again. Yeah, so the maximum here is called to be the rated peak power. So this is very common. So if you want to, for example, find a spec for a motorcycle or a car, usually it's mentioned in the flyer, yeah, the rated peak power. So what is actually means the rated? The rated means that this is the maximum power. Yeah, we call that as rated peak power. And we see here that it's generally increasing. Yeah, it's generally increasing because we understand here that if we want to increase the engine speed, yeah, of course the efficiency will be increasing. Sorry, not the efficiency. The power will be increasing. Yeah, the power will be increasing. So generally in ideal case, if we increase the engine speed, so the power should increase. Yeah, but we see here that for the brake horsepower, yeah, for the brake power here, we see here that at higher speeds, the brake power decreases. Yeah, so it drops directly because now we have to consider friction. Yeah. We've seen before that friction is increasing with engine speed. Yeah, so it's increasing with engine speed. So this means that the brake power now is reduced. Yeah, so friction power becomes significant compared to the increase of the indicated power, so that the rated brake power will drop. And when we look at different size of the engine, yeah. So say here we have an engine which is 3.2 liter, or this is usually called 3,200 cc's, yeah, engine, or 3.2 liter. Here we have a much higher power compared to 2.5 liter. And what about 1 liter is at the bottom here, yeah, the LGCC one at the lower here. Yeah. So it means that the engine size will affect the power that is produced significantly. Yeah. So we see here that here we have a power of about 140 kilowatts. Yeah. And this one almost 200. Yeah. So very large increase, almost 50%. Yeah. So if you look at here, a 50% increase of the engine size creates the rated brake power of almost 50% higher as well. Yeah. And we see here the bottom curve here is the brake torque, the maximum brake torque, or MBT. Yeah, MBT is maximum brake torque. So this is dealing with torque. And we see that it's also have an increasing curve and then return back to the lower value at high engine speed. Now, what is the cause of this one? Because we at the lower speed, yeah, if we have lower speed, it means that we have heat losses. Yeah. So this is dealing with the indicative power as well. So if we have the indicative power at low speed, yeah, at low speed, the indicated power is also low. Why? Because when we have low speed, it means that there are many there will be more time, yeah, more time for the combustion process, yeah, and therefore it will have more time to release the heat. Yeah, we understand that the engine is cold. Yeah, the engine is cold. Yeah, we have a cooling system by the radiator to cool the engine. So if it's too slow, it means that the energy inside will be lost in by the cooling water. Yeah. So if it's too slow, it will have more time to releasing the heat. It means that now the torque is going down. It's lower, very low here, and it will reach the maximum. And when we increase further the rotational speed, it becomes more difficult to ingest a full charge of air again. So this is dealing with how can we regulate the valve to open and close, and doing it very fast at very high rotational speed. So of course, this will cause the efficiency, the charge efficiency or the volumetric efficiency decreases. Yeah. So we see here that it will drop again. Yeah. When it becomes difficult to ingest a full charge of air, it means that it will be the combustion process will not be it not be good as well. Yeah. All right. So that this is a bit explanation of that, and we will look at the mean effective pressure. Yeah, so the mean effective pressure here is dividing the work. Yeah, so we have the work, which is the area here. Yeah, so the work will be the net area, and we divide that with the displacement volume. So that will be the mean effective pressure. Yeah. Okay. So then when we look at the illustration later, wait. So MEP, yeah, is also have two value. We can have IMEP, which is indicative mean effective pressure, or we can also have BMEP. It depends on what work, yeah, what kind of work that is used in the calculation. So if we use indicative work, so that it become IMEP. If we use break work, so that will be BMEP. Yeah. So that because this is measured, yeah, we do measurement from the torque as before, so that we can calculate that to be 2 pi t times NR here is the number of this is a factor which is dealing with the number, how many cycle per number of per revolution, yeah, how many cycle, yeah, how many revolution needed, yeah, yeah, for a cycle, and this is the displacement volume. So that here, if we know the torque, we can calculate the BMEP. Yeah. Okay, so this is the BMEP, and yeah. So this will be the network for one cycle over the displacement volume. So this is the illustration, yeah. So if we have the netto here is this area, so the mean effective pressure is not it's not directly by averaging the pressure here, but instead this area here now becomes this one, yeah, and this will be the mean effective pressure. Yeah, so PR here is the MEP. Yeah, so this area will be as large as this. Yeah, the network for the cycle. Okay, so this is the calculation. And the maximum BEP is obtained at WOT at a particular engine speed. Anyone know WOT here? We have a rated power. We have MBT, maximum brake torque. Now we have WOT. What is WOT?
Oh, wide open
Wide
throttle.
throttle open.
Correct. Yeah, wide open throttle. Yeah, so wide open. Full opening. Yeah, full opening. Of what? Of the fuel, yeah. Fuel opening of the fuel. Yeah, so the maximum BMEP, yeah, is obtained at wide open throttle. So a full gas, yeah, at a particular engine speed, yeah. So this is at wide open throttle at a particular engine speed. So we can be controlling at one speed, and then we open the throttle widely, and then we get the maximum BMEP. And when we close the throttle, this decreases the BMEP, of course. For a given displacement, a higher maximum BMEP means more torque, yeah. For a given torque, a higher maximum BMEP means smaller engine. Yeah, so this is dealing with the equation that we had before. So you can rerun that. And this is important that if we have higher maximum BMEP, yeah, so this is dealing with the material, it means that we have higher stresses and temperatures in the engine. Yeah. And shorter engine life and or bulkier engine. Yeah, means that bigger. Yeah, bulkier is mean bigger. Yeah, so that if we want to have a maximum, a higher BMEP, yeah, if you want to have a higher BMEP, it means that we need to, if we want to be safe, yeah, we want it to be safe, so that we have larger engine. Yeah. And we see here that for the same BMEP, yeah, for the same BMEP, so the same mean effective pressure, two-strokes engine have almost twice the power of four-stroke engine. So yeah, we see here that yeah, the power of the two-stroke engine is higher than four-stroke engine if we have the same PMEP. Yeah. Okay, so this is the illustration. We have IMEP, PMEP. So this is dealing with MEP. We have on the right side here, which is the value here. And this is the indicative power and brake power, yeah, which is shown on the left here. And this is the friction mean effective pressure. So we can do analog to that one, yeah. Analog to PMEP and IMEP, we can also calculate FMEP if you know the power, the friction power here, yeah. Again, the friction power keeps going up with increasing engine speed. Okay, next we have specific fuel consumption, yeah, and this is important as well. Usually it is it's listed, yeah. It's usually how many kilometer per liter, for example. So this is actually specific fuel consumption, in which we can also calculate PSFC or ISFC, depends on what power which is used in the calculation. So if we use M dot here, which is the fuel consumption, the flow rate of the fuel over the power of over brake power, so that will be PSFC. If we normalize it with the indicative power, so that will be ISFC. Yeah, and what we want, of course, the lowest possible SFC is what we want. Yeah, because this means that we have low cost for the fuel. Okay, and this is how it looks like when we have a displacement volume. Yeah, when we have, for example, at the same, for example, same power. Yeah, if we want to decrease the PSFC, we can increase the engine size. Yeah, so we see here that if we increase the displacement volume, yeah, we increase the displacement volume or we increase the engine size here, it means that the PSFC will decrease. Why? Because the heat loss from the gas to cylinder now is being minimized. Yeah. And we see here that the cylinder surface to volume ratio increases with bore diameter. So there is an optimization, yeah, for do we want to make the diameter smaller and large stroke, yeah, for example, small diameter but high, for example, yeah, or we want to make it more larger in diameter, but the stroke, yeah, the stroke distance is not too high, for example. So this is dealing with friction or with the heat loss as well, yeah. So the heat loss to the surrounding, because the surface area of the cylinder that will determine the heat loss, yeah. Okay, so overall, this is how it looks like for specific fuel consumption, yeah. So this is PSFC as a function of rotational speed. And we know here that, yeah, as we seen before, we have a minimum, yeah, the optimum engine speed, in which this will minimize the fuel consumption. And we can see here that we have two curves, in which this is the curve for different engine, yeah. So if we have higher compression ratio, yeah, higher compression ratio, usually with larger engine, yeah, we have lower specific fuel consumption compared to if we have lower compression ratio or smaller engine. Yeah. So we see here that why it has this curve, yeah, why it has this trend. At high speed, PSFC increased due to increased friction, of course. We have known that before, yeah. At high speed, or we should remember that friction will be very high. But at lower speed, again, this is similar to the explanation of the brake power, yeah. At low speed, it has high losses, high heat loss to the surface of the cylinder. Okay, so this is in general, yeah, in which we have additional mechanical efficiency here, yeah. yeah, if you look at what I have in the slide here, the graph will not be similar. So this is taken from different sources, yeah, many sources. And this may taken from one sort of engine, the other from other engine. So, but in general, you can see that we have the similar trend, yeah, the similar trend for the engines. And here we have not the friction power, but what we have here is mechanical efficiency. So it's similar, yeah. At higher engine speed, we know that friction will be significant, so that it will reduce the mechanical efficiency. So we have this sort of graph. Yeah. All right. So I think this is for, yeah. This is just to show you the example of many performance chart of the engine. Now here we have mechanical as well, mechanical efficiency. We have BSFC and here is ISFC. Yeah. And this is for 6-cylinder automotive, 3.8 liter. Yeah. Okay, so this is for gasoline engine, 3.8 liter. Right. Now, the important thing is that we have the term of knocking. Yeah, knocking before. You ever experienced that? Have you ever experienced knocking?
I never had that one.
Huh?
Still don't have experience.
Don't have experience. Anyone experienced knocking before? Have you ever heard about knocking before? What is knocking? Knocking the door? What is knocking? Mungkin bahasa bengkelnya ngelitik. Yeah. Have you experienced of that? Yes.
I've been, man, but a little, man.
A little, okay, ya. Jadi biasanya knocking ini artinya mengelitik ya, mesinnya mengelitik. Pernah merasakan itu ya. Jadi kalau apa? When you push, usually when you put a wrong gear, yeah, you put a wrong gear. For example, you want to have a high torque, but instead you are using wrong gear, higher gear, for example, so that yeah, you will experience knocking. Ya, mungkin sekarang sudah zamannya otomatis semua ya, jadi nggak ada yang merasakan ngelitik ya. Kalau nyetir manual, mobil manual gitu atau motor manual itu sering terjadi knocking. Ya, atau mengelitik, mesinnya mengelitik. So what is knocking, or we usually call that as detonation, ya. So what is actually happened here? So this is still in Indonesia, yeah, but that's fine. Yeah. So if we have on the left side here, yeah, on the left side here, we have an ideal case, yeah, in which in ideal case here we have wait, how to move this? Okay, in which for the ideal case here we have the engine, yeah, and we have a spark plug here which ignite, yeah. So the ideal case is that there will be propagation of flame, yeah, propagation of flame, or there is a wave of fire, yeah, starting from the area very close to the spark plug, and then it will be transmitted away. So there is a continuous burning to the surrounding, yeah. So this is the ideal one. So if you experience this one, so this will be a smooth operation of the engine. Yeah. But when we have knocking or detonation, yeah. But if you have knocking or detonation, so that what happens? This happens when we have a spark plug here which is fired, but then we have other place here which is fired by itself. So there are several fire occur in the region, and it's not in the cylinder, and it's not starting from the spark plug. Yeah. So this is possible that there can be a fuel that is auto burn, yeah, burned by itself. Because why we should remember that the pressure, the compression ratio is quite high, so that the pressure is increasing, yeah, and therefore it can increase the temperature as well, yeah, and it can be auto ignite, yeah, auto ignite, self burned, yeah, auto ignite, not because of the spark plug, and this causes problem. Why? Because we don't have a smooth operation. Yeah, you will experience like bumpy operation there, and this cause knocking on the cylinder, the surfaces of the cylinder, and this can damage the cylinder. Yeah, so this is dealing with knocking or detonation. Yeah, I think if you, I think many of you perhaps already experienced it before. Yeah. Now, this is the assignment for you, is to find, because we are going to talk about knocking as well next week. Yeah. You need to find the definition of octa number. What is octa number? And zeta number. And dealing with that, we have an engine which is called the Cooperative Fuel Research Engine. Yeah. So that will be the assignment for you. I want you to prepare for that. Yeah. Yeah, and you can submit it next week. Yeah, submit it through. It's not clear yet. I think it's through Classroom. Yeah, that will be fine because it's not certain yet what happened next week. So yeah, for now, for the first assignment, we will try to put it online first. Yeah, so you can submit the work before we start the class next week. Yeah, so 3 here, octa number, zeta number, and the cooperative fuel research. Now, try to do search on that and explain what are they. Yeah. Okay. All right. So yeah, we still have time. What time is it? Yeah, it's 12:10. We will continue a bit here. I will show you an example which is provided in the book. Yeah. We will discuss a bit here. So this is, if you have the book already, any of you have the book already? Not yet.
I have it.
Okay. Yeah. Okay. So yeah, some of you already have it. That's good. So we will discuss it here. So this is the problem which is discussed in the book. Yeah. So I will not discuss in very detail, but at least will be an example. Yeah. So here is taken from example 3.2 in the book. If you have the book, you can open it. Example 3.2, in which we have a gasoline engine. So this is 3.2 in the book. We have gasoline engine. Yeah. And this producing, yeah, said to be producing 48 brake horsepower. So it's already mentioned 48 brake horsepower with mechanical efficiency of 80%. Yeah. And it's known that the specific fuel consumption, yeah. Oh, we need one information here. It is very important that this is said to be 4-stroke engine. Yeah, so this is important information. 4-stroke engine, gasoline engine, 4-stroke. Yeah, producing 48 brake horsepower with a mechanical efficiency of 80%. And the specific fuel consumption here is 0.3 kilogram over bhp hour. Now with the air fuel ratio is already known. The air fuel ratio here is 14. Yeah. Now if we have the heating value is 10,000 kilocalorie per kilogram. Now the question is, the IHP, the indicated horsepower, and then P is friction horsepower. C here is PTE. What is PTE? BTE is the efficiency brake thermal. PT, yeah, PT, brake thermal efficiency, yeah, brake thermal efficiency. And D, the brake thermal indicative, or we can say that the thermal efficiency. And the fuel consumption. So M dot of fuel. Yeah. And D here is air consumption, M dot air. Yeah, the fuel, the air consumption. Yeah. Right. Okay. So that here we want to find it. Yeah. For the first question, finding IHP. Now that we can find it from which part? From efficiency. Yeah. We remember that the mechanical efficiency. Yeah. Mechanical efficiency is the ratio between yeah, BHP over IHP. So that if we have the mechanical efficiency is 80%, so that we can calculate the IHP. Yeah, so that we can calculate IHP, that will be BHP over the mechanical efficiency. So that will be 48 BHP, yeah, in brake horsepower. This is the unit, yeah, over 80%, so 0.8. So that we have the result here. The result here is 60 HP, yeah, yeah, or IHP, as the same, 60 HP. All right, so that this is A, so we have that already. Now the question B is finding the friction horsepower. So again, remember, the friction horsepower is the difference between indicated horsepower minus the brake horsepower. Yeah, so that we have 60 minus 48, so that will be 12 horsepower. Yeah, so we have B already. Now question C is to find the thermal brake efficiency. Yeah, so to find the thermal brake efficiency, how to calculate that? How to calculate the thermal brake efficiency?
BHP over fuel power.
Yeah, so that will be BHP over fuel power. Now the question is how to find fuel power. We have BHP already, so this is known. The fuel power will be M dot fuel times the heating value. Yeah. Now the question is, what is M dot fuel here? What is M dot fuel? So we have the SFC. Yeah. We have the PSFC, in which here is in PHP, so that we have PSFC is equals to M dot fuel over PHP. Yeah. Okay. So that if we have PSFC, so that we can find M dot fuel. Yeah, we can find M dot fuel. So this will be M dot fuel. So that will be PSFC times PHP. Yeah. So that we can insert the value. So we have PSFC here, which is 0.3 kilogram per hour per 1 unit of PHP times PHP, which is 48 HP. Yeah, so that we can cross that out. So that will be 48 times 3. That will be 4, 2, 12, 1. Okay, so perhaps like that. Check the value. So this is M dot fuel. So once we have M dot fuel, this is for the consumption, so that we can insert it here. Yeah, so we can insert the value, which is 48 horsepower divided by M dot fuel, which is 14.4 kilogram per hour. Let's check here. And this is times 10,000 kilocalorie per kilogram. Okay, so this is at different value. so that we have to convert it. Yeah, so convert to the conversion. Yeah, all right. So you can find that by yourself. Yeah. Okay, so we have answered C already here. Yeah, M dot fuel is already answered here. Now we have what should be this one? It's not C. A, B, C, D, E, E. Yeah, so this should be E. So we have answered E already. Yeah, and now question D. Is it? Yeah. So now question D, which is the thermal indicative. Yeah, so the indicative thermal. So that will be. So you can calculate everywhere. Yeah, so you can, for example, here from D here. What's yeah, for question D here, to calculate the thermal indicative here, you can calculate it from IHP over M dot fuel times heating value. Yeah, you can calculate from here. So that will be the thermal indicative efficiency. Or we have understand before that we can calculate the thermal break efficiency, which is the multiplication of the thermal indicative and the mechanical efficiency. Yeah, so you can choose either where you want to use. If you use this one, so that you can calculate, we have this value already, yeah, and we have the mechanical efficiency already, so you can find this one. Or you can also calculate this one. We have the value of this, and calculate this one again, similar to this value, yeah, at the bottom here. So that we have the thermal indicator. So either way you choose to calculate, it will be the same result. Yeah, it will be the same result. So you can choose this one, the upper one, or the lower one. Okay, so that is for D. And then last is F, yeah, is to calculate the M dot of air. So how to calculate this one?
Fuel air ratio.
Yeah, correct. Yeah, so we will use the information of the air fuel ratio. So air fuel ratio here is 14. So that will be M dot air over M dot fuel. And this should be equals to 14. So if we want to calculate M dot air, so that will be 14 times M dot fuel. So we have M dot fuel already, so we can calculate M dot air. Okay, so this is example 3.2 in the book, yeah. This is already provided, complete with the calculation. But yeah, be careful when you have that book, yeah. It's not mentioned, it's not putting in the unit. So sometimes it has a constant directly apply in the equation. So be careful with that. That constant is not, cannot be used generally. Yeah. So that constant which appear in the book is only when you use certain units. So it will be better. I would just suggest you to do the manual way here by putting all the units and then do the conversion manually. So that will be safer. Yeah. Okay, so I think that will be all for today. Any question?
Excuse me, ma'am.
Yes.
I just wanna ask for as an assignment we have to discuss before. Is it handwriting or computer writing?
Handwriting. Yeah.
Okay. Thank
Yeah,
you very much.
I prefer to have handwriting. Yeah. Okay, we do it semi-manual, yeah. Semi-manual. So write it in paper and then take photos of it and then upload it. Make sure that you have a good resolution for the photographs, yeah. So yeah.
Thank you very much.
Yeah. Okay. So writing is important. Yeah, writing is important. All right. Okay, so I think that will be all for today. No more questions. Right. Okay, so this will be the end. Thank you for joining the class. I'll see you again next week. We will decide later. Depends on the situation. Hopefully we can meet offline already. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you, ma'am.
Thank you very much.
Thank you,
ma'am.
ma'am.
Thank you.